All right, guys, so today my goal is to give you a little bit of an introduction to logarithms. For SL, this is actually about all that you're going to need. I mean, you're going to be able to have to apply it and things like that, but you're going to get all the basic concepts that you need right now. Okay? For HL, I've got a second video for you today, and then we'll extend it a little bit further next class as we look at logistics and logistic functions and things like that. All right, so we got a couple of things going on here, and hopefully we'll be able to get the basics today. Okay, so let's go right into it. First, we're going to start simply with consider f of x equals 10 to the x power. Okay, what I would like for us to do is we are going to solve this for f of 0, f of 1, f of 2, and f of 3. So if you want to pause it and work through it, then that's fine. Otherwise, I'll go ahead and work through it real quick. I do want us to eventually put this information in the table where we've got x's 0, 1, 2, and 3, and then get our y values there. All right, so go ahead, work through it on your own. And here I go. So f of 0 equals 10 to the 0 power. Anything to the 0 power is 1. F of 1 is 10 to the first power, which is, of course, itself. F of 2 would be 10 squared, which is, touched the wrong one, which is 100. And then f of 3 is 10 to the third power, which is 1,000. So we now have a function, right? This exponential function is one where when x is 0, y is 1. When x is 1, y is 10. When x is 2, y is 100. And then when x is 3, y is 1,000. All right, so this is our exponential function. But the question is, does this function have an inverse? Well, looking at the data that we have and considering the graph that we know exists, the answer has to be yes, right? We know what the graph for this looks like. The graph for this original function looks something like this, right? That's what all our exponential graphs look like when they have a positive base and a positive exponent, right? So it looks like this. It will always pass the vertical line test, which means it must have an inverse. Now, the inverse function, where, this is what the table would look like. We switch the x and y. So if x is 1, y is 0. If x is 10, y is 1. If x is 100, y is 2. And if x is 1,000, y is 3. Originally, there was not a function that described, there wasn't an equation or a mathematical symbol that described this type of function where I could put 1 into it and get 0 out. So what happened is we created one, right? The mathematicians created a function that would do this, and it was called the logarithm. Now, in mathematics, it's usually just written as log with some number as the base. All right. Now, the number for the base is not going to be 0. It's always a positive number. Okay. But the number for the base is generally going to be, at least for SLs, it's either going to be 10 or it's going to be E. Okay, now E is one of those constants, right? E is kind of like pi in that it's an irrational number. It goes on forever and ever, never repeats its digits. You can't write it as a fraction. That's what it means to be irrational, right? It's called Euler's constant, and it can be found in many different ways, but we're not going to go into that today. You can get it on your calculator. E is on there. Anytime you see an E, our assumption is they're talking about Euler's constant. They're not using it as a variable unless they specifically say otherwise. So anyway, this inverse function is the logarithm. Now, if my base function was 10 to the x, then what I use for my inverse function is log base 10. Okay? And so therefore, y would be equal to log base 10 of x. And that is the inverse of 10 to the x power. All right? Now, we don't usually write this 10, just so, I think you are aware of this, but usually what you'll see is y equals log x. And if it's written that way, then it's assumed that the base is 10. Okay, now what I want you to see, if we come back up to our table here, is that this 10 is actually 10 to the first power, right? This 100 is actually 10 to the second power, right? And then this 1000 is 10 to the third power. Now what that means is that when I do a logarithm, right, when I do log x, what the log is doing is it's taking away the base. It's taking away the 10. As long as the base of the log and the base of the exponential match, they will cancel each other out. It's like if I take 3 and I add 2 and then I subtract 2. The add 2 and the subtract 2 cancel each other out because they are inverses, right? If I take 3 and I square it and then I square root it, the squared and the square root cancel each other out because they are inverses. All right, so this is a little bit of an introduction to the idea of a logarithm. It's not anything weird or crazy. It's just the opposite or inverse of an exponential. All right, so what does that mean? That means if y equals 10 to the x power, okay, so 10 is the base. So if 10 is the base, then if y equals 10 to the x power, then what I can do, if I want to solve for x, I can do the opposite of the 10 to the something power. Now, because it's 10 to the something power, I can't just divide by 10 because it's not 10 times x. What I need to do is I need to do the inverse of 10 to the power of x, which is a log 10. So what I'm going to do is I'm going to do log base 10 of y, which I don't have to write the 10, and then I'm going to do log base 10 of x. If I do it to one side, I'm going to do it to the other side. I have to do it to the whole side. If there's pluses and minuses and multiplication, I got to do it to all of that. Okay? Now when I do that, then I'm going to come back here, and now I'm going to have log of y is equal to log of 10 to the x power. Now because this is a base 10 log, because I didn't write it down, we talked about that, then the base 10 log and the exponential 10 are inverses. They cancel out, just like the plus and minus, or the square and the square root. They cancel each other out. They're the opposite, okay? Which means that log y is equal to x, because I've canceled out the exponential, which brings this down as a regular number now, and then the log is also gone, and so all that we're left with is x. And so this is a common conversion, is if you have this, you can always rewrite it as this right here. Okay? Let me show you another example. All right? So another example would be something like if I had y equals e to the x. And like I said earlier, for SLs, this is the only other base you need to worry about is e to the x power. Okay? How do I get rid of that? Well, the same way as before, if I want to get rid of this exponential, then what I need to do is I need to do a log, but this time it's an e, so I'm going to do log base e of both sides. Okay? And if I do log base e of both sides, what I end up with is log base e of y is equal to log base e of e to the x. Now, just like in the previous question, if I have a log with the base and that base matches the exponential, those two functions are inverses. So they're going to cancel each other out. The other thing is log base e, as many of you know, we often write as ln. Okay, the reason why is because we call it the natural log. Now, why it's ln instead of nl, I don't know, but I think it's just because they want it to start with L just like all the other logs. It could also be because the original idea came from a different language where maybe they say log natural. So, anyway, that's what we end up with. So our final answer should be the natural log of y is equal to x. And so this function is then equivalent to our original function of y equals e to the x. Okay, so that's one of the things that you will have to do consistently, is be able to go back and forth between exponents and logarithms. Now, some of this you'll be able to do on your calculator, and some of it you probably won't. All right, so don't worry about it too much, but do be aware of how we can manipulate these variables. Okay, next up, we've got 10 to the x equals 12, and natural log of x equals 3. So we're going to do two things here. First, we're going to solve for it exactly, and then we're going to use our calculator to be able to solve for it approximately. Okay? Now, the first thing to do is, if I'm trying to solve for x, then I need to do the inverse. What I need to do is get rid of the 10. Just like any other function where I'm trying to solve for x, I need to do the opposite, right? So what I'm going to do is I'm going to do log on this side, and I'm going to do log on that side. Because it's a 10, I don't need to write the base down here. It's assumed that it's 10. Okay, now if I do that, what's going to happen is I now have log of 10 to the x power equals log of 12. The log and the 10 to the power of are inverses, therefore they cancel out, leaving me with x equals log 12. Now that is what we call an exact answer, okay? Because we haven't had to round anything, there's no approximations there. That is exactly the correct number. Logarithms are, generally speaking, unless it's an exact number, most of the time they're going to be irrational numbers. All right, and in just a minute, I'll show you on the calculator how to get those. All right, but let's get the exact answer for natural log of x equals 3 first. Okay, so this time, instead of having the exponential, we have a log here. Okay, so the first thing I'm going to do is I'm going to remember that this is log base e of x. You don't have to make this middle step if you don't want to, but a lot of students will find comfort in being able to see the base before they do anything. Okay, my next step in order to be able to get x by itself is to get rid of this log base e. Well, what's the opposite or the inverse of log base e? Well, it's an exponential. So what I need to do is I need to do e to the power of this side. So it's e to the power of all of this. And then I'm going to do e to the power of 3. Because it's e to the power of, not multiplying by e, it's e to the power of that's going to be the inverse of the logarithm. All right? And I have to do it to the whole side. I can't just pop in there and do it to the x. I've got to do it to the whole side. Okay? Now, once I've done this, I do have e to the power of log base e of x is equal to e to the power of 3. Now, at this point, the e to the power of and the log base e are inverses. So they cancel each other out, leaving me with x equals e to the 3. And e is an irrational number, which means it goes on and on forever and can't be written as a fraction. So therefore, this again is the exact answer. All right. Now, if you'll come with me to my calculator, I will show you how to use your calculator to get an approximate answer for each of these. All right. So here we are with me fancy calculator, my TI Inspire. So I wanted to show you how we're going to do the logarithm and the exponential and get some approximate answers. All right. So the first thing we're going to do is we're going to come over here and to get the logarithm, you can see it over here on the left-hand side of my calculator. It's right above the 10 to the x down here on the left-hand side. Okay, so to get the blue thing above that button, we need to push Control first, and then we can push that 10 to the x, and it'll give me log. Now, the basic log is always base 10, so you don't need to put the 10 there. You see how right here the cursor is in the base. You could put a different base there if necessary, but we don't need to put anything there. We just want the regular log. And so here the question we were looking at was log 12, so we're just going to do logarithm of 12, and you'll notice that when I push enter, that it solves it for me, right? It gives me 1.07918. So that's an approximate answer. That is rounded off, okay? And that's it. It will go on forever and ever without repeating digits. Note that it automatically put the 10 in for me, and so that's taken care of. All right. Even if the 10 wasn't there, this would still be a log base 10. All right. The other question that I was looking at on the previous page was x equals e to the third. And you can see that there's an e here. Notice that the natural log is right above it, right there, the ln. Okay, but I want the e to the x, so I just go e to the x and I put a 3 into the box, and then I can push enter and I get 20.0855. Again, this is approximate answer. It is rounded off, right? The number will go on and on forever without repeating digits. It just keeps going on and on and on. It's irrational. Okay, so that's it. We will go back to the other screen because I got another example for you. All right, that's it. And now we're back. This is the last one I want to do for this kind of introductory video, is I want to talk a little bit about earthquakes. This is a real life application of logarithm and exponentials. If you've been watching the news about coronavirus, if you go to many of the websites that have statistics and graphs and things like that will show logarithmic graphs. The reason why is because we start with something that looks like this, right? Because it's a pandemic and the virus continues to increase faster and faster and faster. But if we want to be able to make really good estimates with that, then what we do is something called linearization. Those that are in physics will understand what that process is. Other guys, well, it's okay. You don't really need to know it unless you're in HL, and in that case, I'll teach it to you tomorrow. But what happens is if we turn this from a regular graph, with x and y, into a logarithmic graph, then it ends up giving us, because the logarithm will cancel out the exponential, it'll end up giving us a straight line, which will make predictions a little bit better. But you don't have to worry too much about that. I want you to get a feel, and if you see this online, then that's what you're looking at. Okay. Now, earthquakes. Just last week, there was a 5.7 magnitude earthquake in Magna, Utah, which is about 50 kilometers from where I am staying right now. It was big enough and long enough that it woke up me and my wife and my kids, and we could all feel the house, our beds shaking for 10 to 15 seconds, reasonably large. Since then, there have been almost 300 aftershocks, most of them fairly small. But yesterday there was one that was about a 3.9, okay, which there doesn't seem to be much of a difference between a 5.7 earthquake and a 3.9. But I want to show you what that means and what that is. So the 5.7 earthquake woke me up, but I didn't even feel the 3.9 yesterday. The only reason I knew it was there is because I saw something in the news and I read it. I read something about it online when I was researching about earthquakes for this question. So the question I would like for us to look at is, what's the difference between a 5.7 and a 3.9 earthquake? Well, with earthquakes, this magnitudes are actually a logarithmic scale, okay? And that's the important thing that you need to understand, is that it is a logarithmic scale, okay? Which means that when I go from a magnitude of 1 to 2, that's like going from 10 to the 0 power, 10 to the first power up to 10 to the second power, which you may say, oh, well, that's only 2 times as large. But no, it goes from 10 up to 100, which means that it's 10 times greater. When I go from 2 to 3, that then becomes 10 to the third power, which means that it's now the actual strength is 1,000, which means it's 10 times stronger than the 2, and it's 100 times stronger than the 1. Okay, so you can see the patterns here and how this kind of connects into that idea of the exponentials and the logarithms. So if I want to know what's the difference between a 5.7 and a 3.9, what I'm going to do is I'm going to find the difference in the powers here, right? So I'm going to go 10, and then I'm going to go 5.7, and then I'm going to subtract the 3.9. Okay? And what that is going to give me is that's going to give me the difference in those magnitudes, which I can then turn into, so 10 to the, that would be 1.8. And if I punch that into my calculator, then I get value of about 63. So that explains why one woke me up and the other one I didn't even feel, is because the 5.7 is approximately 63 times greater than a 3.9. So when you start to see those things, I definitely felt the 5.7. Okay, it wasn't really 5.7 by the time it got to where I was 50 kilometers away, but that one I could definitely feel. However, when you see things in the news about like a 6 point something, a 7 point something, right? A 7.7 would be 100 times stronger than what I felt the other day, which would be quite significant. So think about that. When you read about magnitudes and earthquakes, that's what's really happening. All right, and that's enough for today. I think that's enough SLs to get you guys started, and HLs just, like I say, a little bit of introduction to get you moving along. HLs go on to the next video. SLs, you